Well, one, so we have another AIME problem. So this is like number 14. So it's interesting logarithm problem looking, but at the same time, we do have a lot of number theory involved. So let's see what's going to happen. So the a is and x is larger than 1, which is the reason we need to log to define. And we have an equation, and then there is also another equation in terms of x and a given, and then we want to find the remainder when x is divided by 1,000. So it's because of the AIME problem, right? So, but when you look at the equation we are given, especially the first one, because that's going to give us the a. If I know the a, I can get the x somehow. So, but you really want to be careful with the arguments and the base of the logarithm. So we have a parenthesis here, opens there, then a close here. So whatever we have right here is just the argument of this log. And then the good news, at least the base of the logarithm are equals to a, so which is kind of fine. So what I will do first, like I take the log outside log and then convert it to exponential form, because too many logs inside each other, it doesn't look fun. So like if I take this base, and just a quick reminder, if you do have, let's say, the log base x over y is equal to, let's say, t. So then you just take the base of the log, the x to the t power is equal to argument of the log. So that is just the basic of the logarithm, right? So I'm going to use that one in our case. So with that in mind, so like if I take this base to this exponent, I will get whatever inside left over. So that looks like the log base a of, so again, I'm just writing everything right here, of the log base a of 2, and then plus, okay, so plus the log base a of 24 minus 28. So again, this log a so is just gone, and then this is equal to a to the 128 power, because I took this space and put it right here as exponent, like the exponential form. So a to the 128 power is going to be just the argument right here. Okay, but still, this is not really nice looking, but at the same time, we have the base a, and then we also have base a of 2 logs, and we are adding those to it together. So, but this 128, maybe I can remove this on the other side. So if I do this, I will get the log base a of 2 plus the log base a of 24. And then this is equal to 128 and to both sides. So you get 128 plus a to the 128 power. Okay, so now we have the base a and the base a. So when you have the logarithm with the same base, we may multiply their arguments. So the argument is this guy and 24. So if I multiply their arguments, I'm going to get log base a of 24 times the log base a of 2. And I'm going to write the argument in parentheses. And this is equal to 128 plus a to the 128. Okay, this is so far not too bad. But now we have the 24 as a product in front of the logarithm. And then another property that we have the exponent, the power rule. So when you have the number in front, so you can take this as a power of the argument. So we can probably do that. So we can at least have the log base a bit a lot. But before we move on to that one, maybe we can just do the same thing we did with the first step. So we can take this a and then take the a to this guy as exponent. So we can convert this logarithm form into exponential form one more time. So that will give us 24 times the log base a of 2 is equal to a, this guy, to this entire thing as exponent. So that should be look like 128 plus a to the 128. So again, this mess right here is just exponent of the a. So it is not nice looking, but let's see if we can get something out of it. Again, I'm going to pull this now as a power. So that should be the log base a of 2 to the 24 is equal to a to the 128 plus a to the 128. So just keep that a bit clear. So this guy right here is just exponent of the a. And we have the log base a, but there's an exponential form of the base a. So maybe we can take this one more time. So we can take this a, and then a to the whatever power right here is going to be equal to argument right here. So we just did this a few times already. So we did that first time to get this guy, and then we just did right here again to get this one. So we are doing this again. So then 2 to the 24th power is equal to a to the whatever mess right here. So it is going to be a bit challenging. So a to the a, but there is another exponent of this guy. So 128 plus a to the 128. So again, a is the base, and then a to this expression is another exponential form. And then this guy is like whatever we have right here is just the power of this a. But now this doesn't really look fun and manipulate the right side of the equation. So we have like a base a, and then we have some exponent, but exponent a has also another exponent in terms of sum. So when you have sum, we can write the as product of two numbers with the same base, right? So let's try to write something like this. I'm going to keep that a, the bottom a as it is. And then this part of this right side, so it could be written as a to the 128 times a to the 128. So again, this part, it just become basically this one. So this addition just spread that way. Okay, so then, well, when you have something like, this is a number, this is also another number, even though it's missing, we do have multiplication. So if you have, let's say, 2 to the 4th to the 5th, so you can write this as 2 to the 4 times 5, or 2 to the 5 times 4, or 2 to the 5 to the 4. So you can kind of play with that. So like in that case, we have the a to the some power times some power. So you can kind of consider middle 2. So meaning that I can take this guy and then write as power of this, and then as a one number to this exponent. So which can be written as a to the 128 power. So let me write this slightly better. A to the 128 power to this power, which is a to the 128. So I hope that makes sense, and this is exactly what we did right here. So then this is some number to the same number. So and I like to write this number as the same as well. So I can try to write this as like 8 times 3, because 2 to the 3rd power will be 8. So you can write 2 to the 3rd to the 8th power, so which is equal to 8 to the 8. So meaning that one of these actually equal to 8. So the a to the 128 is equal to just 8. Okay, so but that does not really help much yet unless we continue playing with these exponents. So like we have a, which is like power of 2, but this is also 128, that's also power of 2. Maybe that might be useful. So let's think about what we can do, right? So if I want to like take the 128 power of the left side, kind of using this logic right here, let me write here. So if I want to write a to the 128 power, if I want to take the 128 power of both sides, so you got a to the 128. But imagine like this is just one number, even though it's a huge number, and this is another number, and then you got a to the power and to that power. So we multiply these as we did right here, or you can actually swap these numbers as well, right? So meaning that this could be written as a to the 128 to the a to the 128 is equal to, and then I like to write this as well, same power, like numbers to the same power. So the 128 I can try like maybe 2 times 64, because 8 squared is 64 as well. So this could be written 8 squared to the 64th power, and that will be 64 to the 64. So that means 64 will be this number. So the a to the 128 is equal to 64. And I can take the 128 root of both sides. So I can get a, because a is positive number, so we can do this easily. A has to be equal to 2 to the 6 is 64, divided by 128. So let me clean that, 128. And then a is going to be 2 to the 3 over 64. Okay, we did all this work to get something just a. So I hope that was clear. So if something is not clear, so I will say just pause back and then move, like check each step to see if you can miss. So I'm going to clean these because I got a, so I hope that will give us our final answer x as well. Okay, so this is line number 14, so it's kind of expected to get a bit more messy work as well as a bit challenging for sure. So that's a, right? So like the second equation, I can use the same thing. So a to this power is going to be log a to the x is equal to a to the 256. And then if I take this again, so that this to this will be x, so that means x is equal to a to the 256. Okay, so we know the a, so let's go ahead and plug that then. So that means 2 to the 3 over 64 is my a, and then you got 2 to the 3 over 64 to the 256. So I'll start from here. So when you like this is power to this power. So if you multiply this by this, you just get 4 times. So that will cancel. 4 3 is 12. So you got 2 to the 12th power. So from here, so we got 2 to the 3 over 64 to the 2 to the 12th power. And then I can multiply 2 to the 12th by this exponent. So you got 2 to the 3 over 64 times 2 to the 12th. And I can cancel those. So you got 2 to the 6th power, because that's 2 to the 6 times 2 to the 6. So that should give us 2 to the 3 times 2 to the 6. And that will give us 64 times, right? 3, which is 192. So 2 to the 192. Okay, so the x is equal to this number. So we got the x. So now we want to get the remainder of that when you divide by 1,000. So like it's kind of harder to deal with this number. So you can try finding some pattern, but usually what we try to use like the Chinese Remainder Theorem, especially when you are finding the remainder by larger values. And 1,000 is like divisible by 8 and 125, and then GCD of these two is 1. So by Chinese Remainder Theorem, so you can say if you can find the remainder when you divide by 8 and when you divide by 125, then you can use those to get the remainder when you divide by 1,000. So it's kind of something we need to know by the Chinese Remainder Theorem anyway. So like another thing, like let's write that equation. So we want to find the 2 to the 192 This is like, we have a bunch of 2, so that means it's already divisible by 8, so I'm going to say that's 0 mod A. And then I'd like to know what is going to be the remainder if I divide by 125. So 2 to the 192 is equal to x. Maybe I should use different variable. Let's say this is like r mod 125. And you can try finding kind of pattern and stuff, but like I'm going to use the torsion function, so Euler torsion. So if you do not know, so you just take the prime factorization 125, which is, is 5 cubed. So there's a couple ways doing this torsion, but one way is you just take the highest power. So the torsion of 125, highest power is 5 to the 3rd power, and then subtract the one lower power, so which is 5 squared. And then since this has only one prime number, we have only this one. If you had more primes, so you could do this with every prime number. But in this case, this is 100. So why this is going to be useful? Because when you take the torsion of a number, which is 100 in this case, meaning of this, there are 100 numbers that's relative to the prime to 125. Okay, so but another meaning of this, when you take the 2 to the 100 power, okay, so 2 to the 100 power, this will be actually equal to 1 by the Euler torsion, like Euler formula. So we take the 2 to the torsion of the number of the mod is equal to 1, congruent to 1. So why is that useful? So that's mod 125. And if you maybe square this one, because we are going to get like something close to 100, so that's going to give us 2 to the 200 will be also 1. And then I like to multiply this by 2 to the negative 8, so I can get 2 to the 192. And then we want to get that number. So that will be 2 to the 192. And then this is congruent to this one, but I'd like to know what this number will be equal to. If you do know the inverse of mod, so you can actually find the inverse of like 2 to the 8th power, which is going to be something you can do, and then that will give us the answer of this part. But let me do it a bit differently. So this is going to be equal to 1 over 256. And then since we are taking the mod 125, so this, like, if you subtract 250, 2 times of this one, so you get 1 over 6. So that is congruent to this. And then we can immediately add 125 to this number. So they are going to be congruent. So that will be 126 over 6. And then divide by like 2, you will get 63 over 3, which is actually congruent to 21, meaning that mod 125. If you take 2 to the 192nd power, that's actually 21, congruent to 21 when you divide by 125. So we have two things. One thing is divisible by 8. So we already know that right here. Another thing is when you divide by 125 is congruent to 21. So by using these two, I'm going to use the congruency system to solve the final answer. So I'm going to say the n is my number is congruent to 8 times some multiple. So I'm going to say 8 because our number should be a multiple of 8 because it's divisible by 8. Okay, and then that's also 21 more than a multiple of 125. So you can say 21 plus 125, let's say times b. So this is the n. So n is the number we are looking for, something that is divisible by 8, something that 21 more than a multiple of 125. So when you have this kind of stuff, we take the mod, so to remove one of these variables, since the coefficient of a is smaller, so I'm going to take mod 8, so that should be just 0. Congruent to, if you take the mod 8, so that's 16 plus 5, so which is going to be 5. And then this is going to be 120. 120 is divisible by 8, so that means this is going to be 5b. So the mod 8. So like if I want to take this, subtract 5b from both sides, so you get negative 5b is congruent to 5 mod 8. So you can easily see if you choose b is negative 1, then that would be 5b congruent to 5, which does work. So b is congruent to 1, negative 1. So that means b is equal to negative 1 plus some multiple of 8. So I'm going to call that's just k. K is some integer. So we take this b and then plug back right here so we can get n. So the n is equal to 8 times 8, which is something has to be multiple of 8. But also it's equal to 21 plus 125 times b, which is negative 1 plus 8k. And I don't really care about this one because that's obvious. It has to be multiple of 8. But if you look at the second part, so you got like 21 minus 125 plus 125 times 8 will be just 1,000 times k. So when you simplify this, you get actually negative 104 plus 1,000 k. So it's telling us the n, which is the number we are interested, is multiple of 8. Okay. Also, negative 104 plus 1,000 times something. So if I choose k is like 1, that will be 1,000 minus 104, which is actually equal to 896. So that's the smallest number that is actually like the largest number, smaller than 1,000. So you can have like more numbers for n, but we are looking for the remainder when you divide by 1,000. So then n has to be 896. So that's our answer. So again, in this problem, we kind of did a couple of things. One thing was like using the logarithm properties was a bit painful, especially when you have a lot of exponent. So which we really want to know how to deal with the exponent powers when you have more than ones and stuff. That is like what we had, even though they were not really too different. So it's just a bit more like interesting looking. That was the one thing we kind of had to deal with. As soon as we realized x is like 2 to the 192, I mean, yeah, x is this number, we want to divide that by 1,000. So at that point, we really want to use our number theory stuff. So we use like orders like Totient to use like some what power of that 2 is actually going to be 1, which was 100 of Totient of 125. Well, we use 125 and 8 because we kind of want to know what would happen if we can find the smaller mod so we can deal with, and then we can combine those by Chinese Remainder Theorem, which is basically showing that congruency is the Chinese Remainder Theorem. Okay, and then we got the answer for 896. So anything that you kind of feel like wasn't like really clear, so I will say review those backgrounds. So I'm going to add some stuff in the description so you can review those, just get some background if you need it. Okay, anyway, I'll see you in the next video.